Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. I'm Ian Wolfe. On this summer edition, we visit the Wayback Machine and uncover the authentic sounds of 2003 in genuine low fidelity. We have stories on legal psychology, retinal displays, human compasses, and chili. Ever wondered how to use science to make friends and influence people? In 2003, Christine Baker spoke to social psychologist Kip Williams from Macquarie University about the science behind the tactics lawyers use to win their cases in the courtroom.
Supreme Court, 10 a.m., 8th of August, 1985.
Your Honour, I have a confession to make. My client did drink before driving.
Order in the court.
It may sound like a good reason to fire your lawyer, but stealing thunder, the practice of revealing potentially incriminating evidence before anyone else gets a chance, is a tactic lawyers use all the time to get their clients off the hook. Social psychologist Kip Williams from Macquarie University has been studying the psychology behind courtroom tactics. I asked him how stealing thunder works.
It makes the side that reveals the information first seem more honest. Revealing the worst thing about the client, they're not trying to hide it. And we know that people like honest people. They're more likely to be influenced by the side that they think is more honest and more credible.
The honesty factor is a big reason why the stealing thunder tactic is successful. But Kip Williams says his most recent research found an alternative reason why the stealing thunder tactic works.
When you steal thunder, it sort of surprises the jury, and they don't quite think they're hearing things right. And it's as though they're saying, this doesn't seem right, this seems like it would be bad, yet the side that is working for the client is the one that's revealing it. Maybe I'm misunderstanding this, or maybe it really isn't as bad as I thought. And so what we find is they sort of rework the information, the thunderous information, until it has a slightly different, less damaging meaning. Most attorneys say that the reason it works is because it allows you to put your own spin on it first, so you can kind of discount its impact or say, but this isn't really so bad. But we found that although that can work like that, in our research it's actually better not to give any spin in whatsoever. Just flat out say, my client drank a six-pack of beer before he went driving, and not to try to diminish it or put a spin on it. And what we think happens there is that the jury, as I said before, they're surprised by this, and so then they supply their own spin. They give reasons why this must not be really so bad.
But the stealing thunder tactic isn't foolproof. In fact, Kip Williams says the best way to make it backfire is to tell the jury they've been duped.
One way to make it backfire is for the other side in the closing arguments to say, ladies and gentlemen of the jury, I just want you to realize that the defense used a tactic on you called stealing thunder, where they revealed the worst piece of information about their client before we did. And they know that this tactic makes people not be as affected by this negative information. And so basically they were manipulating you.
Oddly enough, lawyers haven't rushed to denounce each other for stealing thunder in the courtroom.
I've never seen an attorney do that before, and I've seen a lot of trials where they do steal thunder. If you remember the O.J. Simpson trial, both sides were stealing thunder constantly in that trial. Of course, if you reveal the tactic about the other side and you're using it yourself, then you'd be hurting yourself as well.
It seems the courtroom is a veritable hothouse of psychological manipulation. But exactly how much impact do tactics like stealing thunder have on the verdict in a trial?
Well, I think it depends on how much evidence there is or how damaging the evidence is. I think all of these sorts of things, these tactics and other social influence factors, are not going to be very important if the evidence is overwhelming. It's when the balance of the evidence is close, so people are wavering on that beyond a reasonable doubt threshold. That's when these sorts of tactics can push people to one side or the other.
Are there any other kinds of situations where people use tactics like stealing thunder?
Interestingly, in the law arena, attorneys always use stealing thunder, but can you think of the last time where a politician used it? No. It's curious, isn't it? But, you know, in America, had Clinton admitted to the public that he had had a sexual relationship with Monica Lewinsky and that he was sorry and that the rest of it was between him and Hillary, I have a feeling that would have been pretty much swept under the rug. And we did some research that not only found that voters would say they would be more likely to vote for somebody who stole thunder than for whom the thunder was revealed by somebody else, but journalists and editors and reporters indicated that they'd be less likely to follow up the story and to devote more attention to it if the candidate stole thunder. So it seems to us that politicians ought to give this a try.
Social psychologist Kip Williams from Macquarie University spoke to Christine Baker about the psychology of law and order. Apple called the iPhone and the iPad displays retina displays, but that's just marketing nonsense. Keir Smith explained how if you're rich like the military, you can have movies shown right on the retina of your very own eyeballs.
We're all familiar with TV and the conventional computer screen based on the CRT or cathode ray tube technology. We're also familiar with flat screens and LCD or liquid crystal display monitors. Some of us have even seen or used head-mounted displays, which are kind of like goggles with little LCD monitors inside. The next generation of display design, pioneered by a research group at the University of Washington, have invented and quickly patented a VRD, or a virtual retinal display. Perhaps inspired by the seminal Neil Stevens book, Snow Crash. If you've not read it, I suggest you do so. With a VRD, a coherent light source is utilized to scan images straight onto the retina of the viewer's eye. Although scary and a little dangerous in my opinion, this approach has several advantages. The display's resolution is not limited to how small an individual pixel can be made, like in conventional monitors, so it can display a very high resolution image. Also, the display's brightness is controlled by the brightness of the laser beam used to display it, so it's bright enough for use in the outdoors even on a sunny day. And the display can operate in either an immersive or a see-through mode. The first VRDs were designed for use by fighter pilots in the military. They formed part of an AR, or augmented reality helmet, where information was superimposed on the visual spectrum. This allows a computer to show the pilot where things are, put up crosshairs perhaps, or show important statistics about the plane they were flying. For good virtual reality, you need to track the head movements closely, so that you know which direction the person is looking, so you can show the images that correspond to where they're looking in this virtual world. Now with augmented reality, head tracking is even more important, because you need to superimpose images over what the person can see. So if you want to highlight an enemy fighter, for example, if the pilot moves their head to the right, this AR system must be able to move the highlight to the left and keep the crosshairs trained on their target. I won't go into the head tracking technology because there's not time today, but I will tell you how VRDs, or virtual retinal displays, can actually work. Although not the only one, the VRD developed at the University of Washington uses two oscillating mirrors to deflect a beam of modulated laser light onto a 2D raster scanning pattern. Now, raster scanning is the technique used by your TV or a conventional computer monitor. It's when a beam of light is focused to display one pixel at a time, starting from the top left-hand corner, then moving across the top of the screen. This is repeated line by line all the way to the bottom. Now, if you do this fast enough, i.e. about 26 frames or more a second, your eyes turn this series of scans into a moving image. But I digress. So this modulated laser beam is passed through a spherical mirror, which lines up and then focuses the beam before it enters the eye. At any one instant in time, only one pixel from the raster scan is being illuminated on the retina. Nonetheless, the viewer sees a stable image because the image is being updated so fast, i.e. 26 frames a second. So, just before the light enters the eye, it is reflected off a partial mirror to provide an augmented or see-through display. The best VRDs offer a staggering resolution of 1355 by 960 pixels, which is about as big as one of those sexy Apple cinema displays. But to buy one of those, you'll have to win the lottery first. For now, people like you and I will have to stick to watching TV on a box in our living room. But perhaps one day soon, we'll be able to slip on a pair of Ray-Bans and watch The Simpsons projected onto the backs of our eyes.
And thanks to Keir Smith, if you had in-flight movies projected on the backs of your eyes, you could have one for each eye. You're listening to Ian Wolfe on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. In 2003, Keir Smith had been talking with his Uncle John, who has an absolute sense about where the poles are.
That's right, Tim. I was talking to my Uncle John. It turns out he has an amazing sense of direction. Probably one of the finest I've ever seen. In fact, he has a remarkable polar sense. He can always tell you which way is north. But when he travels in the northern hemisphere, which he does a lot, his sense of north is 180 degrees out. His intuition for which way is north now suddenly points south. I thought this was curious, so I decided to have a little search around and see what I could find about large-scale human spatial perception, what we call sense of direction. My research into sense of directions for humans uncovered a few interesting morsels, the most remarkable of which is a study done on the natives of the Central Caroline Islands in Micronesia. It seems that they could travel for several days, over hundreds of kilometres of ocean, with no way of keeping their bearings except for, say, the colour of the water, the direction of the wind, the clouds and the stars in the sky, and they always ended up where they intended. One master navigator said, "Well, I just paddle and the island comes to me." Other hands-on studies include a South Australian group who blindfolded their students and drove them round and round for 20-odd kilometres to a place about 5 kilometres where they started. The sun had set and they wore earmuffs. It turns out very few of the 35 subjects could guess the direction of the journey's origin, where they came from. But, on the other hand, the subjects were amazingly accurate in guessing the direction of their homes. Strange but true. So what does this tell us about the human sense of direction, I hear you ask? Well, I don't know. No one really knows. But there are some excellent theories, like the one we have magnetic particles in our nose, which help us tell which way is north. Which is why we're able to come home to our home, in the same way a homing pigeon can. Homing pigeons, incidentally, have tiny deposits of iron oxide in their head. This oxide is known as manganite or lodestone, and it's the metal that was used to make the first ever compasses. Now, in defense of these scientists who believe that we have magnetic deposits in our heads, when the same experiment was done with those blindfolded students was repeated, only this time when they had helmets with magnets in them, they were driven round and round and round and asked to point towards home. Most of them failed. But think about this for a second. These scientists put on earmuffs, blindfolds and magnetic helmets on their students, then drove them round and round and round after dark. Well, I think it's no wonder that these pretty little kids were a tad disorientated.
That was Keir Smith following his nose to find north. These days you could buy a southpaw to gently buzz against your ankle on the side that's facing north. In 2003, self-confessed chili addict Adam Mark reported on when pain is a good thing.
When I was young, our family had a chili bush in the backyard. My brother and I were told not to go near it because the chilies were of an extra hot variety. So just like when someone says to you, don't think of pink elephants, our curiosity got the better of us, and we decided to pick the chilies off the bush and throw them at each other like any 5- and 6-year-old would do in a similar situation. So after a good 30 minutes of this fun and frivolity, the call of nature, well, called. Gentlemen out there in Radioland, I don't have to draw you a diagram on what happened next. Suffice to say that I spent the next hour in a very cold bath trying to deaden the pain. So since that eventful day, I've been strangely fascinated with the humble chili and its tear-jerking effects. You see, the compound that provides the kick is called capsaicin and is found mainly in the interior tissue of the chili, which is where the seeds adhere to. Capsaicin has at least 5 separate chemical components, or capsaicinoids. 3 give the sensation in the throat and the back of the palate, while the other 2 give a slower, longer-lasting sensation and less fierce sensation on the tongue and mid-palate. The chemical responsible for the chili's sting was first isolated by an Englishman in India in 1877 and later identified as 8-methyl-N-vanillol-6-nonamide. Since then, researchers have isolated a dozen or so individual compounds that make up capsaicin. Each capsaicinoid differs slightly in chemical structure. Essentially, each structure is a hexagon attached to an open zigzag chain of carbon atoms. The hotness diminishes as the chain lengthens or shortens, suggesting that there is a midpoint at which hotness peaks. This may explain why some peppers have an immediate bite, while others only cause moderate discomfort. The perception of heat is felt when the chains get to be 3 or 4 carbons long and disappears when the chain is longer than 11. The hottest range seems to be 8 or 9 carbons in length. The increasing understanding of how capsaicin acts on a chemical found in nerves called substance P, by the way the P stands for pain, has created a surge of interest amongst neuroscientists. Extensive experiments with animals show that capsaicin relieves pain first by selectively attracting and then destroying the messengers responsible for taking the pain messages to the brain. When capsaicin is applied to the body, it first attracts substance P from the nerve endings at the contact point. Substance P then starts to signal a burning sensation to the brain, but capsaicin soon begins to destroy the attracted messengers. As more SP is sent, it too is destroyed. Capsaicin bleeds the neurons of SP until they no longer manufacture it. As a result, there are no more pain messages left when capsaicin has been applied, and the sensory nerve endings become insensitive to chemically induced pain. What is extraordinary, according to these scientists, is that capsaicin destroys only the pain messengers and leaves intact the nerves, others charged with relaying tactile sensation, like physical pain, heat, cold, taste, things like that. Such is not the case when anesthetics are administered or when a nerve is severed to relieve chronic pain. Pharmaceutical companies are finally beginning to exploit this unique attribute of capsaicin, which has long been the active ingredient in muscle relaxants and topical creams. But how do we objectively measure the hotness of a chili? Like rocks have Mohs scale of hardness, chilies have the Scoville scale. The Scoville scale refers to the number of times that extracts of chili dissolved in alcohol can be diluted with sugar water before capsaicin can no longer be tasted. It was developed by a pharmacist named Wilbur Scoville and became known as the Scoville organoleptic test. Scoville had been studying the pharmacological uses of the chili, but became frustrated with many variables. Complaining in the 1912 issue of the Journal of American Pharmaceutical Association, Scoville felt it would be better when ordering peppers if their pungency could first be ascertained on a measurable scale. He knew that the tongue was the most sensitive area able to detect capsaicin, but the compound responsible for the pungency in peppers. Because capsaicin is soluble in alcohol, Scoville was able to soak them and attract the pungent chemicals from the pods. From this extract, he took the precise measurement and added definite amounts of sweetened water until the mixture's pungency was barely perceivable on the tongue. In the case of Japan chilies, it took sweetened water in volumes between 20 and 30,000 times the pepper extract before the pungency was barely discernible. Thus, he rated those chilies as 20,000 to 30,000 Scoville heat units. This system was used until the invention of a machine that could detect the hotness of a chili. Another way to measure the potency of a pepper is to use a high-pressure liquid chromatograph, or more commonly referred to as an HPLC machine. Unlike humans, it never tires of testing chili pungency. To test by HPLC, capsaicin is put in a tube under high pressure and then exposed to a beam of light. Since capsaicin fluoresces, that is lights up, the stronger the hotness of the pungency of the chili, the brighter the light. This measurement is then transposed onto a graph, which looks more like a seismograph, complete with peaks and valleys. Capsaicin is actually composed of several individual compounds, with each representing a unique type of pungency. The peaks of all the curves are added to designate the chili's strength. While the tongue was able to test only about 6 samples per day, the machine is able to do 30 samples in 8 hours. Although the American Spice Trade Association is a strong proponent of the machine, Scoville's name is so well established that the association has had about as much success in making people adopt their scale as the US government has had in adapting the metric system. According to Scoville scale, the following peppers range from the mildest to the hottest. The Anaheim, between a measly 250 and 1,400 units. The humble jalapeno, between 3,500 and 4,500. Tabasco, 30,000 to 50,000. The Cayenne, to 100,000 to 105,000. And the mother of all chilies, the habanero, which averages 300,000, which is pretty much lethal. Ironically, capsaicin is odorless and flavourless. It is barely soluble in water, so although drinking water when you get a good hit feels good, it does bugger all to break down the chemical components. But capsaicin does dissolve in milk fat or alcohol, which is why many hot dishes are served with a milk dish or should be consumed with copious amounts of beer. But that's another story.
That was the Red Hot Chili Pepper himself, Adam Mark, reporting on capsaicin, the active ingredient in chilies. Many people consider science and scientists to be pretty strange. What they don't know is that sometimes these scientists wear that strangeness as a badge of honour and battle for the title in a kind of science geek street fight. In 2003, Chris Stewart reported from the front lines of this turf war of the weird.
Recently I had the pleasure of participating in a public debate at the University of Sydney between the schools of physics and chemistry. The point of contention was over which subject was the weirder of the two. When I started my research for my argument that of all the sciences, physics is truly the home of the bizarre, I assumed that the subject matter was where the weirdness lay, but I quickly found that a rich vein of weirdness runs through the generations of physicists as well. I don't know if it's whether the subject that makes the people weird, or if it's the other way around, but there's certainly a bloody good correlation. Back in 1566, an astronomer and Danish nobleman named Tycho Brahe was a student at the University of Rostock in Germany when he got into a duel with a fellow student. The fight wasn't over some bitter love triangle or anything as gauche as a sour financial deal, no. Apparently, these two were bickering over some small mathematical disagreement. During the duel, Brahe lost his nose, sliced clean off. Since microsurgery hadn't been invented yet, the best he could do was fashion a new one out of precious metal. Brahe spent the rest of his days with a gleamingly polished gold and silver honker. But that's just the beginning of Brahe's weirdness. He also kept a pet moose, or perhaps it was an elk. Reports differ on this detail. The moose died sadly one day after sneaking into Brahe's castle, drinking loads of beer and falling down the stairs, breaking all its legs. James Prescott Joule was the guy who discovered back in the 19th century that all the different kinds of energy, like heat and electrical energy and mechanical energy, they're all really different kinds of the same thing. And that energy can be transformed from one kind to another. And so obsessed was Joule by these ideas that he spent a good part of his honeymoon studying energy transfer in a waterfall. Most people just have sex. Joule figured that as water tumbles from the top of the waterfall to the bottom, some of its gravitational energy is converted to heat energy. And he tried to test this idea by taking along on his honeymoon a large and very precise thermometer to measure the water temperature at the top and at the bottom of the waterfall. Sadly, because the water breaks up so much as it falls, he couldn't take an accurate reading. Astoundingly, despite this peculiar post-nuptial behaviour, the Joules went on to have a couple of children. Joule also did many experiments with electricity, including several featuring his household staff. He subjected one young servant to increasingly powerful electric shocks until she fell unconscious, at which point he stopped the experiment since he could no longer measure the shock's effect. But perhaps the weirdest physicist of all was Richard Feynman. Feynman won the Nobel Prize in 1965 for his work on bringing together the physics of light and matter, relativity and quantum, the theory known as quantum electrodynamics. But Feynman is almost equally famous for a lifetime of strange behaviour. Feynman worked on the Manhattan Project, the unparalleled gathering of scientists, technicians and government spending that brought about the first atomic bomb tests in the first half of the 1940s. Despite extraordinary security surrounding this topmost of top-secret projects, Feynman managed to break into most of the safes in offices around the project compound, swapping secret documents for love notes or pot plants. But one of the best examples of his peculiar lust for life was in his music. Feynman taught himself to play the bongos and recorded several percussion pieces with two colleagues, calling themselves the Three Quarks. One song in particular that stands out, an ode to one of Feynman's lifelong passage, his morning glass of orange juice.
That was Chris Stewart with just a few examples of why he's not doing physics anymore. And that's all from us this week on Diffusion. Would you like to hear your voice on radio? record a voice memo on your phone, or use the voicemail tab on the Diffusion website. We need more people contributing stories to Diffusion. Send your contributions, opinions, helpful suggestions, and donations to science@diffusionradio.com. That's science@diffusionradio.com. And please do send me an email so I know you're listening and would like to hear more episodes. Please like the Diffusion Science Radio page on Facebook and rate us on iTunes. Tell your friends. Follow me on Twitter @Ian Wolfe. Join my patrons in supporting the show at patreon.com/diffusionradio. Contributing to the program from 2003 were Keir Smith, Chris Stewart, Adam Mark, and Christine Baker. Sound check and fact checking by Charles Willock. I produce Diffusion, which is broadcast around Australia to 27 stations on the Community Radio Network, including 2 RBM in the Blue Mountains of New South Wales, 8 CCC in Alice Springs and Tennant Creek, 2 NVR in Nambucca Valley, and 3 MBR in the Mallee Border districts of Victoria and South Australia. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to our podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos, and videos about this week's show. If you enjoyed the show, you can explore more than 900 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Subscribe to the Diffusion YouTube channel at youtube.com/c/diffusionradio. I'm Ian Wolfe. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.